I mean, everything about water, the problem is solved, is what most people think, because after all, water is perhaps the most prominent substance on the face of the earth. But what about the cloud? It's also made of water, and how come it floats? So this is one question. Most people really never thought about it. They see clouds floating, and well, okay, it floats. When it gets the urge, it'll jump from the branch into the water, and it walks on water, as this National Geographic video. How does that work? So I decided to write a book, and the idea was to present Gilbert's ideas in palatable form.
Have you ever wondered how water is structured? Well, in this video, we're going to get into it. You're here with Mark Boutwell and Jared Pollock on Perfect Gardens TV. Please remember to like, share, and subscribe. And if you haven't checked us out on Instagram and Facebook, please make sure to do so. Remember to check out our $2.99 membership. Over 115 growers ready and willing to assist you through your growing practices. Make sure to hit the join button on the bottom of every video.
Okay, so I want to talk about the fourth phase of water. I'm going to try to convince you that this phase is really important for your health, and also it plays a role in agriculture. I know some of your listeners are interested in that subject. And I'm going to be talking also about a surprising role of light. We don't usually associate light with water, but I'm going to be trying to convince you that light is absolutely central to what goes on with water. So water, I guess water is a subject, and I guess I couldn't start without showing this beautiful painting. Okay, and so most people think that water, I mean, everything about water, the problem is solved, is what most people think, because after all, water is perhaps the most prominent substance on the face of the earth. I may be missing something, perhaps there's another, and it's a simple molecule, but so the presumption is, yeah, sure, by now scientists have been studying this for centuries, so everything about water must already be known. So I want to start with a few examples of issues that we really don't know and don't understand, to demonstrate to you that there's a lot to be learned about water. Okay, so here's the first question. Why do clouds float? Now, if you were to take a long ladder, one that extended all the way up to here, and you had a pitcher of water, and you turn the pitcher over, what happens to the water? Well, of course, obviously, it comes down like a waterfall, right? But what about the cloud? It's also made of water, and how come it floats? So this is one question that probably most people really never thought about it. They see clouds floating, and well, okay, it floats. Second question. The water is evaporating from this body of water here, and it's evaporating from here, and it condenses here into a cloud. But what about here? Why is there one cloud here and no cloud here? What's special about this region? And next question. Okay, so here's an experiment done by a colleague, but we've repeated the same thing. You take 2 beakers of water and you fill them almost to the brim, and put the lips of these two together, and put one electrode in the left one electrode in the right one, and impose a high voltage. This is what happens. First thing that happens is you get a bridge between the two. But what's even more interesting is if you take a motor and move one away from the other, the bridge persists. And it'll persist indefinitely, and up to distances of 3 to 4 centimeters. How do you explain this? Ordinary water doesn't, I mean, you don't expect it to behave in this way. And if you don't know the answer, parenthetically, even the people who do this experiment for a living don't really know the answer, then you don't really know about water. Okay, here's another one. This is a lizard. Lizard lives in Central America. I'm not sure which country, but it may be Costa Rica. Sits on a branch like this, and when it gets the urge, it'll jump from the branch into the water, and it walks on water, as this National Geographic video demonstrates. And so it's called the Jesus Christ lizard because it walks on water. How does that work? And again, if you don't know the answer, you don't know about water. This one is one of my favorites. So I actually saw a demonstration of what you see here about a decade ago, presented by Shogo Ueno from University of Tokyo. So what he does is he takes a container, a trough of water, and he puts in a red dye, red for the reasons that will become obvious in a moment. And behind it, he puts a superconducting magnet, and it's a really powerful magnet. When he turns on the magnet, the Red Sea split so that Moses could walk across. So, I mean, how do you explain that? This is a demonstration that anybody could see. So interesting that the magnetic field on the water causes the water to separate in this way. Amazing. Anyway, so those are a few interesting observations that almost nobody really can explain. And so the major point is we really don't know about water, or we don't know enough about water. We may think we know about water, but there's a lot to be learned. I got my inspiration from this guy, Gilbert Ling. Gilbert came from China, and after World War II, there was a decision made that China would send its most promising scholars to the U.S. to study. And they got together from the whole country. They picked three. One was a physicist, one was a chemist, and this guy was the biologist. And they searched from throughout China to pick the most promising ones. The physicist went on to win a Nobel Prize. And they all thought that this guy, Gilbert, was the cleverest of the three. And Gilbert never won a Nobel Prize, but many people think he should have gotten at least 2 Nobel Prizes. One of the main reasons was that Gilbert was studying water, especially water in biology, water in the cell. And Gilbert came to the conclusion that water in the cell is not like water in the glass, that in the water in the glass, the molecules are both randomly oriented and flipping around at some fierce number of times each second. Interesting. But he said, no, it's not like that in the cell. In the cell, it's different. He said that the molecules are actually lined up like soldiers at attention. And he wrote several books on this subject. And of course, it was a radical hypothesis. And I met him at a conference in Budapest, and I was so impressed. I was impressed not only by Gilbert and what he presented, but I was equally impressed by perhaps a dozen colleagues who had evidence of their own that fit this general paradigm. So I got really excited about it because I knew that if this idea, if really true, changes everything. So I gave one of his books to a few of my favorite students and postdocs in the laboratory, and every one of them came back with pretty much the same opinion. This is amazing. They said, if this guy is right, all of biology is changed. And so they reinforced my impression that this is really important. And so we had been studying, my field was muscle contraction, contraction at the molecular level, how the proteins interacted to produce force and motion. And we had to change because this was just too important. Even after spending a couple of decades pursuing muscle contraction, water seemed to be more central. So I thought, well, what am I going to do? First thing I decided to do is write a book. And the reason for writing the book, Gilbert had already written a bunch of books. I think by the time he died, it was like 7 or something like that. He'd written it, but Gilbert had a tendency to write more or less for himself. He could understand it perfectly well, but for others, it was a real challenge. Gilbert, I think, would sit down at the typewriter or word processor, go to it, send it to the publisher, and that was it. Whereas many of us would edit, rewrite, get critique, et cetera, et cetera. So it was a real challenge to read and understand what Gilbert had been writing. So I decided to write a book, and the idea was to present Gilbert's ideas in palatable form. And I think I somewhat succeeded. I went even beyond what Gilbert had been saying. I think I succeeded because the reviews were polarized, and some said, this is just nonsense. It just is a reiteration of Gilbert Ling, and everybody knows that Gilbert Ling is a crackpot, so pay no attention to it. You know how that goes. And other people were really enthusiastic. One guy from Harvard, and of course, if it's Harvard, it must be right. He wrote, this is a 304-page preface to the future of cell biology. That one I liked. So the reviews were, as I say, mixed, but I got to tell you that the really discerning people will pick this book, there it is, we'll pick this book out among all others, as you can see here. And, you know, and in this particular case, this is, he's still reading. He might need glasses or something like that, but, you know, it's taken him some time and he's trying hard to digest it. So anyway, discerning readers are really interested. So we decided to shift our field to explore this really interesting field. And it started with Gilbert Ling's idea. We wanted to do some experimental studies and wound up demonstrating that, well, the general idea of ordered water, structured water, as Gilbert called it, is correct. The details are different, somewhat different from what Gilbert had been suggesting, and I'll explain that. So here's Gilbert's idea in a nutshell. Inside the cell, you got proteins and other solids. And on the surface of the proteins, most of the surface is hydrophilic. That is, it's got charges sitting on the surface, and these charges interact with the water. So each one of these is meant to be a water molecule taken as a dipole, a plus here, minus here, and so on. So you can imagine if these charges are arrayed on the surface, the first dipole would stick here and another one here, and in between them, you'd get other ones that were lining up and so on. And you might expect these to the next layer to line up in a similar way. But we know about thermal motion, Brownian motion. Eventually, everything is disordered. Eventually. So what does eventually mean? Well, according to physical chemists, there are maybe one or two of these layers adjacent to the surface, but beyond that, everything is random. But Gilbert said, no, it's not true. He said the evidence shows that there's order that can extend out to hundreds, if not thousands of layers. And obviously he was controversial. And by the way, what I'm going to be showing you is that hundreds or thousands is a gross underestimate of the actual number of ordered layers. So anyway, that's where we started, and this was maybe 15 years ago that we're thinking, how do we approach this experimentally to figure out, is this right, is it wrong, is there more to it? And we took it. We came to realize, why is it? Yeah. So when you have order, like a crystal, this is a kind of liquid crystal. Liquid crystals tend to exclude solutes and particles and practically everything. Otherwise, they wouldn't be pure. It's like ice. You know, when the ice forms, it pushes out all of the impurities that are in it. Or you can see, for example, at the lip of a glacier, after the ice is formed, it pushes out all the debris, and you can see it right at the bottom of the glacier. So the principle is similar here. There should be, wherever you have this kind of water, ordered water, it ought to exclude pretty much everything. And so that's what we began looking for. And we found it. I'm sorry, this is...
No, it's okay.
Okay.
May I ask a question while I was working through the delay?
Absolutely.
So this, maybe I'm referencing this, but this kind of looks like a like a magnetic like, do you know magnetic coils, like how they work, where they're constantly flipping from positive to negative to create a magnetic charge? And the way I look at this is the white side is like a net. Am I correct? The white side's like a negative charge, and the blue side's like a positive. And so when I look at this, it's like it's constantly, are these molecules like constantly creating like magnetic charges by the constant attracting and repelling of the positive and negative charges?
Well, if they were moving, but Gilbert Ling's idea is that they're not moving, that they're stable, stationary. You see, and if they're stationary without that kind of movement, I know what you're alluding to, that if you have moving charges, they create a magnetic field. Like if you have current flowing through a wire, then there's a magnetic field that's created around the wire. This is not like that. If it were moving, yes, absolutely. But if it's not moving, then it's static. And the consequence of that is that these molecules would basically stick to one another and line up, unless thermal motion, Brownian motion, is disrupting that kind of order. And that's the current or the accepted view among physical chemists. So they don't buy the idea, or many of them, most of them, they don't buy the idea that there could be water molecules sticking to each other like that. Is that clear? Or
yeah, no, yeah. Perfect. That really just hands down just kind of points me in the right direction, keeps me following you properly.
So the first set of lights I purchased were Enfun, a brand called Enfun, and I actually got 2 sets of those. They were 240 watt light panels, 2 panels equaling 240 watts. And after that, the other ones I purchased was Leno Focus.